Hello everybody. This class is a bit outside of the other lectures, and what is goal? It's about seeing some examples of what we have seen so far in a more practical setting. So you do not have any practicals this year because we cannot do them, and we can though do something on the computer. And typically what we use in this context is we use MATLAB and Simulink, which is a part of MATLAB. So I'll just go back to recap some of the examples of the past lectures from lecture 2 to 3 and 4, and we just try and draw them into Simulink as block schemes, and we see actually what they mean in practice. We try to get some diagram and to get a little bit of a gist of what's going on when we draw something on the board or on the paper. So for a start, let's look at this one. It was in class number 2, slide 14. We start by saying that a dynamical system is some kind of box with an input and an output. So let's just try and get this thing done in Simulink, and then we can try different inputs and different outputs, and we try to understand what this means. So let's go to MATLAB. Here you might have a different version than me, but more or less what I say is the same for all versions with some small aesthetic differences. You can launch Simulink by just typing Simulink like this, or otherwise you find it somewhere in the bar over here. I just type it. So here is Simulink. Simulink is a graphical based simulation tool which allows you to simulate a dynamical system, linear, non-linear, whatever, just by basically drawing something that looks a lot like a block diagram. So to create a new model, just click here, blank model, and then after a while you will see a new page opening, page with nothing written on it. We need to wait a little bit. There we go. So blank page. How do we fill it in? Well, you need to click on the library browser. What is the library browser? Basically, it's the collection of all the blocks we can put in here. So as we've seen before, block diagram is a set of arrows and blocks connected together. And here in Simulink is not different at all. Basically, you have some blocks and some connection drawn by arrows, and blocks can represent dynamical system, or they can represent source of signals, or they can represent tools that you might add to visualize or operate on the signals. And the arrow represent the signals themselves. Signals can be scalar or vectorial. In this case, we start with some scalar, and sometimes this is a bit tricky in Simulink because it's not so obvious to distinguish them just by a look. So let's try to do this thing over here. Just one block, input, output, see what output we get as a function of different inputs. And in order to choose a system for it, we just take a first order system, and we see what's the step response, for example, for a start. So let's go for it. We need to first create the dynamical system. We just go into continuous, which stands for continuous time, and we look for a transfer function. There we go. We just slide it inside here and drop it in the blank page. Please feel free, of course, to stop the video anytime, take your own version of MATLAB and redo what I'm doing so that you can try it yourself. So transfer function, now we just have a standard transfer function 1 over s plus 1, but that's not what we want. We want to have the function over here, which is k divided by 1 plus tau s. So basically how we do it, well, I invite you to double click on it and read very carefully the instructions. That's good in general, in order to understand how to complete this block. So basically you have, in this case, to complete the coefficients of the numerator and the coefficients of the denominator in the descending order of power. So if you have a denominator, for example, order 1, the first is the coefficient of s, and the second is the coefficient of s to the power 0, descending order powers. And if you only have, of course, one number, then it's a scalar. So in our case, we have a k at the numerator. What is k? Well, we'll think about it in a minute. And we have at the denominator, we have what we had? We had 1 plus tau s. So we have tau and 1. Now, of course, you see that he's not very happy that we have put some numbers that he doesn't know. What is k and what is tau? Variables, and we can define these variables in MATLAB. So that's the trick. Basically, when you launch Simulink and you define variables, you can define these variables in the MATLAB environment, and Simulink will see them. So we just write k equal 10 and tau equal 1. There we go. Tau is a time, remember, is 1 second in this case. So now we filled it in. You see it, if you zoom a little bit, you can even see the transfer function written explicitly in literal form over here. We have it, k and tau have been defined, so no problem. Now we just need to complete the picture by adding a step as an input and something to visualize the output. So in order to get the input, we need to create a signal, and for this we need a source. We click on the source sources here in the library, and we need a step function, which is here. The step function needs to be specified as well. You can connect the arrow with the input of the dynamical system. So double click again, always check what's inside. You have a step time, an initial value, and the final value. So step time is the time at which the step will happen, so the signal will go from something to something else. So initial value is the first something, and the final value is the something else. So basically defined as you see it here, this step will go from 0 to 1 at time 1, which is fine for us. Sample time, for now, we do not change it, but it's basically says at which level of discretization the signal is generated. Of course, this simulation tool is inside the computer, so a computer cannot really keep in memory continuous type signals, because it would mean to have an infinite number of samples to memorize. So of course it always works with sampled signals, but it tries to hide this as best as possible. So in most cases we can just forget that the signals are sampled and believe that everything is continuous, even if it's not true. So we have it. We have a step. We have our system here, and now we want to connect it to something that allows us to visualize this signal, the output. So how to do it? Well, we go to the Sinks tab here, which means something that can take a signal and keep it. And typically we take the scope. Scope means just a screen on which you can visualize your signal. And there we go. We just done. So now I can zoom, open the window to the maximum. So we get everything shown here, and you see you can just run your simulation like this. Pay attention. You have the duration of the simulation over here, and if you wish, you can also change the properties of the simulation by clicking in the model settings here. Typically, in the model settings, you have the solver that is used for the simulation, which means which numerical method is used to get the solution of the differential equation. Because remember, this thing basically is the graphical implementation of a first order differential equation in this case. Well, we just trust Simulink that the choice is correct, so we do not change this for now. We just double click on the scope in order to visualize the signal. Now there is nothing because we haven't run any simulation yet, but the window should open. Let's see, and then we can run it. There we go. As soon as we run it, we'll see something appearing there. don't know where it went. It takes some time. The simulation is being compiled, and then we will be able to see the results on a duration of 10 seconds. There we go. This is the result. So you can see for the first second from 0 to 1 nothing happens, because this step actually changes from 0 to 1 at 1. So nothing everything stays at 0 before, so nothing happens. Then at a certain point this starts to move, and we have, as you can see, a first order transient. As you might remember, the settling time of first order transient is 3 tau. We chose tau to be 1 second, so after 3 seconds we have basically reached the 95% of the final value of the function, which is 10, which is the, as you remember, is the gain times the final value here, so k times 1. We can also visualize the signal, the input signal itself, if you like. We just copy the scope. You can do it by left clicking and dragging it away. So this is another scope. You just create a new arrow starting from the end and then connecting over here, and you can double click on this one to show it. Due to the fact that the scope is new, you have to relaunch the simulation in order to visualize it. And this is just basically the picture of the step, what goes in. So this is what goes in, and this is what goes out. We have visualized first order transient, and we can try any other kind of signals which we might want. So I invite you to realize this very simple system, very simple model in your version of Simulink, and then try and run it yourself and try to change the parameters, change the values of the constants, for example. We can do it here, no problem, just as a trial. Let's see what happens if I take tau equal to 0.1. Let's run it again. Do not forget it. Run it again, otherwise the things will not change. This is still the old result. We run it again. You can do it with the button here or even with the button here. So you see we still have a first order transient, but it's a lot faster because tau is 0.1, so the settling time in this case is just 0.3 seconds. So as I said, please try and make it yourself, and try to change the different parameters and see what happens. This allows you to give you a gist of dynamical system, what they mean and how they work. And you can also try second order systems just by clicking over here and adding an extra value in this term. Another thing you might like to do is to add labels here and then. So for example, this step is if you click here, you can give it a name. For example, this is what we call U. You can give a name also to the output, this Y, and also to the scope. But unfortunately, you cannot give the same name to the blocks, so sometimes you can just be happy with putting labels somewhere. You just double click in any location and you can add a label. U. Oh, sorry, I didn't want to do that. Just double click and create an annotation. There you see, for example, Y. There you go. That's it. So these notes, these annotations are very useful for commenting your model in case you want to pass it to someone else. This is my first Simulink model. There you go. Okay, so please have a try, and then after you tried, you can move on with this video, and we'll see another example of what we can done, and we basically check one of the examples of the class on Simulink. Okay, we move on in 3, 2, 1. I just delete everything, so I have a new page. Which example we move on? We go to this one of the third class, slide 28. We have seen an example of feedback loop And if you remember, we discussed the stability of this feedback loop as a function of k, the gain k. So what we will do first? First, let's just write this function as input-output, and let's just see what it does. And then we'll extend the model to the whole closed loop, and then we'll see actually what happens for different step inputs of C, for Y, what happens changing K. Let's see. So let's start. This is H, so we just created by, as we said, transfer function block. So let's just get back to the library. We take a source, we take a step. In this case, as we are working in open loop, this is a step of what we call U, which goes into continuous transfer function. There we go. And then scope sync. So this is what we call H. So what is H? Let's look at it over here, otherwise I'll forget. So double click, remember, write the coefficient, so 1 at the numerator, then coefficient of s to the power 3, 1, coefficient of s to the power 2, 16, coefficient of s to the power 1, 68, and then last coefficient of s to the power 0. And you can check yourself if you did it right just by expanding the block, and you see the literal expression appearing over there, which confirms that we did it just right. Okay, so I'll call this one U. I'll call this one Y, and there we go. So we can see actually what happens. Let's just write a 40 second test. What happens for this scope if we run this with this system just in open loop? I'll also write here an annotation to remember that this is H. Okay, let's run it. So we just get this transient, which is of course it is not a first order transient. You can see here it starts flat, so it is typically at least second order, and then it goes flat to a final value, which tells us that basically the system is input-output stable, is a BIBO stable. We have a bounded input, the step is bounded, and we get a bounded output. So H is stable, and of course we can also check it by checking the poles. As you remember, we can just write this down in MATLAB. Just do like this. We create the Laplace variable, then we declare H as 1 divided by the literal expression written here, so s power 3, 16 times s power 2, plus 68 times s, plus 80. Then with the command pole, we can just check the poles, and they have all negative real part. So this confirms again what we just saw, that the system is input-output stable, or BIBO stable as you prefer. So now let's complete the picture with this feedback loop. So how to include the feedback loop? Well, if we include the feedback loop, then U is not free anymore, so we just have to get rid of this step, and U will be the result of another block. Considering that the block in this case is just a scalar output, we can a scalar gain, sorry, we can just use the block gain in the commonly used blocks. It's this one. It looks like a triangle because this is the symbol that in electrical circuits they use for gains. So this is our gain, and we just write K inside, and we didn't define K yet, so we see this error message over here. I will do it in a second in MATLAB. So we just write K equal to 1. Remember, the MATLAB is case sensitive, so if you write capital K or smaller case k, it is not the same. We still have the big K equal to 10 from the last example. So let's continue. here what we get, we have, as you can see here, the difference between C and Y. So we have to create this difference, and for this we use a difference block or a sum block. Still from the library, we look into math operations. We look for the sum. There is also a subtract if you like, but this is more generic. You just copy it, you take the one you like, connect it, and then we need to change this sign to a minus sign. We have plus and plus, so you just open it and change the second sign to minus, and actually you can put as many signs as you like, and you will have as many inputs that you like for your sum and difference, for your algebraic sum. So here we get C, and C now is any signal, our reference set point, let's say, and so we plug a source, which will be a step again. But you can feel free later on to try any signal that you like. Again, a step going from 0 to 1 at time 1 if we do not change these values over here. So let's just write some annotation to remember this C. This one was called epsilon, is the difference between C and the value of Y, and then we need to connect Y over here. Remember, always doing backwards. You will never be able to take an extra arrow from an arrow, but you have to start from the input of a block, draw the arrow backwards and connect it to an existing arrow. So there we go, we got it. I just compressed a little bit in order to make it more readable. There we go. Epsilon is here, C is here. So let's see, we define k equal to 1. If you remember the example over here, for k equal 1, we had a stable system. So let's see if it's true. Let's open this scope. This is still the old result because we haven't run it again. So let's run it again. We have a bounded signal. So bounded input. The input this time is C. The output is bounded. Let's try the other values. If you remember the example, we had that the closed loop system is stable for k smaller than 1008. So let's just try 1000 to see if it's true. Let's run it again. This is still the old one, so we need to run it again. Oh, you see, we get a strange result. So it takes a lot of time, but you can see that sooner or later it's going to converge to a final value. But still, you might notice that the response is starting to be a little bit problematic, and we don't like this oscillation over here. Let's see what happens if we go beyond this value of 1008. So let's just pick k equal 1300, for example. Let's run it again. Now, according to our study, the function should be the transfer function should be unstable, and there we go, it is unstable. Check the scale over here, it's huge. So bounded signal generates an unbounded signal, so the system is not Bebo stable. But pay attention, from U to Y nothing changed, so H is always the same, it's always stable. So pay a lot of attention of the difference between the loop transfer function, which is k times h in this case. So this one does not change because of the loop. What changes is from C to Y, okay? And the link between the loop transfer function k times h and the closed loop function from C to Y is given by the both criterion, if you like, the Nyquist criterion, as you might remember. Okay, if you don't want to do the computations, you can just straight away see the limit between stability and instability by drawing the Bode diagram of the loop transfer function and checking if it satisfies the hypothesis of the Bode criterion. But this has already been done in the class. Okay, so again, please feel free to try this yourself and change whatever you like to change. make sure that you have an understanding of what this means and what has been done, so that the class will make a little bit more sense to you. Okay, please feel free to stop the video, and then when you're ready, run the video again, and we go to another example. In 3, 2, 1, let's go. So which is the other example we want to see now? Well, example from lecture 4. Let's take one of these, for example, this one. Let's try to see what is the response, for example, for a unit step at C, and then for a unit step at P. So we have basically, again, a closed loop in here. So it looks a lot like what we already done in the previous example. We have an extra signal going in here. So we basically need to put an extra summation node over here and to change, of course, these blocks. So I just slide this one over here so I can see it. I just slide this one over here and change this one into this one. So this is already the same. We just need I will zoom backwards. We just need to replace the transfer functions. So this one is just 1 over s. You can just basically write 1, 1 and 0 if you like, or otherwise you can just look into the library and you will find in continuous the integrator block. It's up to you. Well, let's just put the integrator, and we use this one for a transfer function, for the other transfer function. We just put it here. And then we still have another transfer function to put into the picture, which is this one, 2 divided by 0.5 s. 0.5 s plus 1. Okay, there we go. I'll make it a little bit more compact so it's easier to read it. There we go. There we go. Epsilon c and zoom in. Okay, now we need to add another summation node over here. So I just delete this arrow, copy this block over here. You can actually change the order of the sign if you like it. Nice, you just do like this. Then we need the plus and the minus sign. It should be okay. I know I got it wrong, so it's the other way around. Minus, plus. There we go. So we just connect it and put it there, and at the input we'll have another step, and this step of P. If we want to see the two steps, the effect of the two steps separately, then we need to be able to turn these steps off in case of need. So typically, if you want to change something very quickly, just by doing some trials by hand, you can use a block called manual switch. You find it in signal routing over here. So basically, its visual is very, how to say, self-explaining. You can connect. Oh, no. I lost this one here. You can basically connect one signal to two different signals, and the choice of which one is connected is done by simply double-clicking on the manual switch. So what we connect over here? Well, basically we connect a 0. So we can choose between this one and 0. And the 0 we created by a source, a constant source. We just double click on the constant and write 0. There we go. We do the same for the other input P. There we go. P, there we go, and 0. You could have used actually the same 0 if you wished. It would have required an arrow going around here. Okay, there we go. So what happens now? Well, we can check if the results are what we expected. So what do we expect? Well, let's just leave C as input, the unit step of C, and P as 0. So if we look back at what we've done here, from C to Y, we should have a 0 steady state. So let's open the scope. This is still the old scope, so this doesn't mean anything. We need to run it again because everything has changed in order to see the new result. We have a final value of 1, which means that the error is 0. Actually, we should visualize also the error. This is the epsilon error here. We said this will yield 0 error, so let's visualize. The error goes to 0 exactly. So it's exactly what we predicted. We have a final value of y due to c equal to 1, which means that the error is 1 minus 1 equal to 0. So let's show them a little bit more properly. Okay, this is y, and this is the error. We can just change the names here, error, and this is y. So like this, the scopes will have the names written on top, y and error, exactly as predicted. Now let's see the other situation, so where c is 0 and p is non-zero, and if I'm not wrong, we have predicted a non-zero error, so basically yp is minus 0.5, which correspond to an error of 0.5 because c is 0 as well. So let's open the scopes again and we run it again. This is again the old values. Let's see what happens now in the new situation. We have, as you can see, minus 0.5 for y and c minus y, 0 minus 0.5 equals 0.5, exactly as predicted. So if you feel like it, you can just try the other examples and see if we get what we expected. Otherwise, you can just bear with me and we move on to the last example of this tutorial practical class. Will appear in 3, 2, 1. So we just move to this one basically, which is not different from what we have done before. We just need to replace the transfer function. What I would like to show here is again the passage between stable and unstable closed loop as a function of k. So let's we already done this one, but let's do it again. So let's take MATLAB. So we define h as 15 divided by s plus 5 square. We have let's take k equal to 1 for now. We have c equal to k divided by s. F is equal to 1, so we don't need to worry about it. The loop transfer function for negative feedback is c times h. So let's see in the case of k equal to 1. So let's see what is the gain margin of this function. We just bought it of L in order to see whether the closed loop is stable or not. So we just write read on. So as you can see, this picture over here, when we hit minus 180 degrees, the function has a gain which is a lot below 0. So if for k equal to 1, we are closed loop stable. But if k increases, you remember the curve would go up. So basically we have more or less minus 24 dB. So it means that we can go up 24 dB before we cross the line we should not cross. So 24 dB means that k can grow up to 10 to the power 24 divided by 20, sorry, like this. So it means that for k up to 15.8, more or less, because we did it graphically, for k up to this value, the closed loop is stable. And for k beyond this value, we get an unstable system. So let's verify this by the use of Simulink. So let's draw this one, which is exactly the same as before, just we have to replace C and H. So H is basically integrator, sorry, C is basically integrator times K, so we can just exchange the functions in the old example here. So let's clean it up a little bit. So this one, just so this one is K divided by S, so it's like this. I'm not wrong, right? K divided by S. Then we have 15 divided by S plus 5 squared. So 15 divided by S squared. 10, sorry, 1, 10, and 25, which is S plus 5 squared. So there we go. Just clean it up a little bit. So here we go. Connect. Sometimes it's a bit difficult to connect the arrows. So K divided by I got it wrong here. It's like this. K divided by S. 15 divided by S plus 5 square. Okay, no problem. This now is called R, where whatever, and this now is called D. Well, we don't care so much about it. In any case, it doesn't matter which one of the signal we let in, because the stability of the loop doesn't change with respect to the output. So they will be unstable or stable regardless of which one goes in. So we did it. So in this case, for K equal to 1, everything should be stable. So this, again, the last example, we run it again to see if this is the case. So we have an input in D. As you can see, bounded input generates a bounded output, and namely 0, which was probably easy to guess because we have an integrator over here. We can exchange actually the input and run it again, and we see the same. The system is still stable and the error is 0, as you can see. Right? Very well. We can also leave the two signals on at the same time, and you basically have by linearity the summation of the two effects. Where you go? No problem. So let's try now K equal 15. By what we said, 15 should still be okay. So let's try again. Let's run it again and see if the system is closed loop stable. Yes, it is, but you can notice we are getting close to the danger, which is given away by this oscillation over here. Last, let's try K equals 16. Try it again. Well, we are not so much unstable yet, because I remind you we done this in a approximate way. So let's try a little bit further. K equals 18. Try it again. There we go. For 18, we are definitely unstable. So I think that's all for today. I hope you got the basic gist of Simulink and MATLAB. Let me know if you want to know more. We can probably do more. And that's all for today. I hope you enjoyed. And everybody, please stay safe.